like to talk with you about the invention and development of reference point indentation. As shown in the first slide here, the reference point indentation started from a desire to measure the properties of bone, the material properties of bone. How easy is it to fracture bone or not fracture bone? And so it started with an automatic center punch. The automatic center punch, it turned out, would make deeper indentations into baked bone, which was weaker, than into control bone that was stronger. And so the automatic center punch could distinguish between weaker bone and stronger bone. But how could you do this in a patient? The next slide shows the first reference point indentation instrument. Now in this instrument, you can see that there's a test probe. This is the probe that would be indenting the bone. The distance that probe went into the bone would be measured relative to the position of the reference probe that sat on the surface of the bone. So this way, the skin could be penetrated and the distance of indentation measured even though the bone was still hidden below the skin. This particular instrument, it was the first one. It wasn't the last by a long shot because it had a problem with tipping. If you tipped it, it changed the readings a lot. So the next thing we realized was it would be better to use a hypodermic needle as the reference point, because that would be closer to the indentation point, wouldn't be so sensitive to tipping. And then the indentation point could run down the center of that hypodermic needle. Now this is called a probe assembly for reference point indentation. For a patient, it would be intended to be single-use disposable. And it turns out that a lot more went into it than just a hypodermic needle. It turned out that it was important to sharpen the reference probe just so, and bevel it and so on just so. But it started with a simple hypodermic needle. This shows some of the prototypes went through, starting with that automatic center punch I showed you, going to the prototype next to it, which was the first reference point indenter, and then a series of them that used the hypodermic needle. The first ones that are shown there, the first 12 of them were basically built in my garage over a period just of a couple of months. After that, tried to get serious and measure more carefully the details of the force versus distance curve and built reference point indenters like the one that's called prototype 15 there. It shows me with a graduate student, Georg Fontner. This was the largest reference point indenter ever built. Shortly after that, when we figured out what was needed, we were able to reduce the size of everything down there to prototype 19. This slide shows prototype 19 in action. What you can see is that if I put a bone under this probe, I could turn the instrument on and it would measure complete force versus distance curves of indentation into that bone. And I could take a piece of simulated soft tissue, in this case just a piece of red rubber. I could put that on top of the bone, could go down through that and measure the properties of the bone as if that soft tissue weren't there, because the reference probe still sits on the surface of the bone and indentation distances are still measured there. So now we had an instrument that it looked like it would be possible to use on patients to see if material properties were important predictors of fracture risk. Alex Proctor and Davis Breimer entered that instrument in a new venture competition for the technology management program. Now, this is a program at UCSB where talented undergraduates present ideas to investors at a fair, and these investors invest play money in the inventions that they think would make the best companies. At the end, whoever gets the most play money wins and gets real money. In this case, Alex and Davis won. There's their check, most fundable idea. They used the money. It turned out they convinced not only the mock investors that this was a good idea, but most importantly, they convinced themselves. and decided to actually start the company. And so they started the company, which at the time was called Active Life Technology. It's now called Active Life Scientific. You can see what happened to them next. They ended up in Barcelona under the needle. There's Dr. Adolfo Diaz Perez, a wonderful, wonderful physician who really wanted to test this instrument. As soon as he heard about it, he was very excited. He wrote a grant overnight to the Spanish government to get one of these instruments and try it, because he knew in his hospital, he's head of internal medicine, he had a lot of patients who were in bed with hip fractures, and he had a lot of patients of similar age who were in bed for other reasons. And he really wanted to see whether he could distinguish the bone of those patients whose bone had broken from the bone of patients that did not break. But we had to start out figuring out how to measure on humans. And so here you see Davis being tested at the moment with the instrument, and Alex waiting in the background to be tested next. With the help of these human volunteers, procedures were worked out on how to measure patients, and we started measuring patients. Each one of those dots represents an elderly woman laying in a hospital bed, either with a hip fracture in the case of the black dots, or without a fracture in the case of the red dots. It turned out it was much easier to find women in hospital beds of the elder with fractures than without. You can notice there's more black dots than red. This is a huge problem for elderly women, the hip fracture, because it lays them in hospitals for extended periods of time during which they can get infections. They have to lay on their back, can't even turn on their sides. It's a horrible decrease in the quality of life, and it really can inhibit their ability to lead an active life. It's a great human tragedy. What I saw in the first patient that we measured was that their bone was incredibly more easily indented than the bone of Davis and Alex and myself that had been measured as trial subjects. And this followed through. It turned out that on the x-axis is a measure, on the y-axis is a measure of how easily how far the indentation went in, and you can see the black dots are higher than the red dots. That means that the patients with hip fractures, their bone was more easily indented with this instrument than the patients without hip fractures. In fact, everyone whose indentation was greater than 40 had a fracture, and everyone whose indentation was less than 30 did not have a fracture. In between 30 and 40, there's some of each. So it's not a perfect distinction between the two groups, but excellent. And so this is the basis of reference point indentation. And it's exciting to people now because for the first time, they're able to measure bone material properties in patients, and it's then possible to use this same instrument in laboratory experiments to decide how to improve bone material properties in a way that's known to be relevant to human fracture risk. Thank you.